I'm just starting the video, the YouTube live. So now we're live on YouTube. We should be. I'll check. Okay. Okay, so we have 25 participants in the room. Okay to start? I've already texted Nathan. He'll probably join in a few. Sige. Good morning, everyone. Hindi ko kayo maisa-isa. Medyo madami tayo. But welcome. This is parallel session 2.2 entitled Electronics, Electrical Engineering, and Instrumentation, which officially should start at 8:30 or 8 o'clock. I'm not sure. There were some few changes that went around. Kung 8 o'clock ba o 8:30 magsisimula. But here we are. They can start at any time. And welcome to the PAASE, or the Philippine-American Academy of Science and Engineering 40th PAASE anniversary, and also the 2020 annual PAASE meeting and symposium, or APAMS. Okay, we have 3 speakers for this parallel session. We have Dr. Rafael Jaculbia, Dr. Nathaniel Hermosa, and Dr. Marianette Morales Vega. The first speaker is Dr. Rafael Jaculbia. Let me please give a short introduction. Dr. Rafael Jaculbia is a special postdoctoral researcher at the Surface and Interface Science Laboratory in RIKEN, located in Wako, Saitama, Japan. Raf obtained his PhD in physics degree at the National Institute of Physics. From 2011 to 2014, he was an instructor here at NIP and taught introductory and advanced courses in physics. In 2014, he became an intern under Professor Satoshi Kawata through the RIKEN's program for junior scientists. And he was also the Edgardo Gomez Awardee for Outstanding PhD Graduate way back in 2016. His fields of interest are nano-optics, plasmonics, of course, terahertz spectroscopy, instrument development, scanning, tunneling microscopy, and atomic force microscopy. And his talk will be on a recent work that his group did on single molecular resonance Raman effect in plasmonic nanocavity, which was published in Nature Nanotechnology just this year. So this is a very new work. So without further ado, let me welcome Dr. Rafael Jaculbia to talk about tip-enhanced Raman spectroscopy and imaging of a single molecule in ultra-high vacuum and low-temperature environments. We have muted the participants of this meeting, but if you have clarificatory questions, if you may unmute yourself, and so as not to disturb the thought of the speaker, may we request the audience to please restrict your questions to short clarificatory questions, and more and questions that would require drawn out discussions, let us reserve them after the talk is done. So without further ado, let me welcome Raf. You may start anytime, Raf.
So again, I'm Raf from RIKEN. So I'm very happy to be invited, although I didn't initially know that the talk should be this long, but I will not talk for 45 minutes because I cannot. So again, I'm from RIKEN, and I'll discuss our recent work on tip-enhanced Raman spectroscopy in UHV, ultra vacuum, and low temperature environments. So probably, as I said, I cannot talk so long about these results. So I thought I should introduce RIKEN. So RIKEN is short for Rikagaku Kenkyusho. So for us, it's totally meaningless, but for Japanese, it's obvious. The meaning is obvious. So in Japanese, this is the characters. So you can read this Rikagaku Kenkyusho. Then basically, it's Butsuri or physics, then Kagaku or chemistry, and this is institute. or research place, actually, literally. So officially, it's Institute of Physical and Chemical Research. So our institute, it's not a university; it's a research institute. Institute of Physical and Chemical Research. That's why actually, uh, one research scientist in our group once said that why are there many bio research in RIKEN? Because RIKEN is supposed to be Physics and Chemistry Institute. Why there are so many bio? Anyway, so RIKEN, of course, anywhere in Japan is beautiful. In April, here is a photo of our just a pond in RIKEN. And as I said, RIKEN is not a university, but a research institute. So the division is a little special, a little different. So RIKEN is separated into mainly, they said, three main clusters. So RIKEN's cluster for pioneering research, where we belong. Basically, this is anything. So the research topic is anything and only based on the direction of the PI or the principal investigator. Then there are still traditional research centers, like they call it the strategic research centers, which are basically mission-oriented centers. Like its mission is on advancement of photonics or materials, mathematics, brain science, sustainability, just traditional research topics. But also there's a so-called research infrastructure. This is the user a shared large-scale equipment, basically. So like supercomputers or free electron lasers and other things. So that's RIKEN. And as I said, as I continuously say, RIKEN is not a university, but actually RIKEN has a so-called program for junior scientists, where RIKEN can accommodate students. There is so-called International Program Associate, where here foreign students are allowed, foreign students can be supported by the program who are enrolled in either a Japanese university or a foreign university. Actually, UP, NIP has a memorandum of agreement for the International Program Associate. So RIKEN can accommodate students from NIP. And then they can do the research in RIKEN and obtain the degree from UP. Also, it's possible to be a junior research associate. This one is only for Japanese or foreign students enrolled in Japanese universities. So if the student is in a Japanese university, then he or she can be a JRA and still work in RIKEN, but the degree is given by the Japanese university. Also, so these are for students. I belong to a special program called Special Postdoctoral Researcher Program. So this program is basically a postdoc program for Japanese and foreign research fellows. Actually, there's more programs in program for junior scientists for PI, for example, young PI. So, but I thought it's not so interesting for our related for this for other people. So I just want to advertise, if interested, you should ask your advisor if you can do research in RIKEN. So as I said before, I am from Surface and Interface Science Laboratory. Our laboratory is headed by Dr. Yusuk Kim. Right now we have about more than 20 members. So one is Dr. Kim, and then 5 scientists, several postdocs and students, and some only 2 technical staffs and 1 secretary. And as a trivia, at one point we had 4 Pinoys: Celine Catalan, Katz, then Mimi. She is the first IPAC of NIP RIKEN. Then Vani also belonged to SISL ones, but now she is in a different group in RIKEN, and myself. And as I always say, there is one feeling Pinoy in our group. He is watching now, my boss, basically, Dr. Hayazawa. So our group as our group's main tool is actually the scanning tunneling microscope, STM. And the STM we use is in ultra high vacuum and low temperature. And the mission of our group, I got this from our website, is the study of energy transport and conversion at solid surfaces and interface in the nanoscale regime. So the STM is a very powerful tool for studying metal or substrate molecule interactions with spatial resolution up to the angstrom scale. So some topics our group are doing now are this. So plasmon-induced reactions in the single molecule scale, or on-surface synthesis of new materials. So making the new molecular assemblies in the surface. And yeah, I am involved in development of new tools for nanospectroscopy, because basically the STM is very good for topographic measurements. So you can see the molecule, individual atoms, in fact, but you cannot identify them. So it is basically blind. But it's strange because you can see nano objects, but basically it doesn't know what those objects are unless you support it with some form of spectroscopy or some form of calculation. Traditionally, just some form of calculation, but very recently, STM groups have been trying to develop tools together with the STM for spectroscopic experiments, optical spectroscopy especially. So if you're interested, you can check our website and some recent publications here. So as I said, I am part of the group developing new tools for nanospectroscopy. Especially, I am assigned to work on tip-enhanced Raman spectroscopies. So I thought just a brief review of Raman spectroscopy. So for example, if we have a molecule, simply diatomic molecule, then this molecule has some electronic states and vibrational states. This is not drawn to scale at all. So if we shine light to this molecule, then this molecule can be excited to a so-called virtual state. And eventually it relaxes. And this radiation is scattered. If it is scattered, then we call this radiation Rayleigh scattering. Then in the case of Rayleigh scattering, the energy of the incident light and the scattered radiation is the same. And majority of the scattered light is Rayleigh scattered, so no change in energy. But one in, I don't know, 10 million or something. So very few of the scattered radiation can be scattered inelastically. That is, the molecule is excited to the virtual state and it doesn't relax to the original state, but is instead relaxed to a little higher vibrational state. In this case, this phenomena is called the Stokes-Raman scattering, wherein the energy of the scattered radiation is different from the energy of the incident radiation. Also, the molecule the molecule can be in an excited, not excited, but a different vibrational state than the lowest electronic state. Then it relaxes to a lowest energy state. Then this is so-called anti-Stokes-Raman scattering. Basically, both are Raman scattering, just the energy of the spectrum is different. Then also, it's possible to have excitation enough to excite the molecule to a real electronic state, not a virtual state. And then in this case, so the molecule is excited to a real electronic state. Then when it comes back to not its original state, then this is so-called resonance Raman scattering. So basically, the excitation is, as I said, enough to reach the actual electronic state. So Raman spectroscopy is very strong to identify the target molecules because the vibrational states are unique to a particular mode, a vibrational mode, and by studying the combination of these modes, you can identify the molecule. So as a short example, for example, we have this fairly simple molecules, and structurally they are the same. So this is a phthalocyanine molecule. It's used as a dye. So these two molecules. So this is a phthalocyanine molecule with nothing at the center, and this is a phthalocyanine molecule with a metal on the center. This metal can be several things. For example, iron, zinc, copper, magnesium. Now, if you see this, they basically look the same to us, especially to physicists. But when you want to see what molecule this is, basically you can do Raman. Just put this molecule on the sample plate, then shine light and detect the Raman signal. And in fact, you will see that these molecules have very different Raman spectrum. So of course, since each of these Raman modes represent a vibration, a particular vibration, there can be common Raman modes between these two molecules because they are structurally the same. But as you can see here, the intensities are different and there are slight shifts of the Raman signals. And with this information, you can identify each of them. So based on the spectrum alone. So as I said, the identification of similarly structured molecules is no problem for Raman spectroscopy. And we always say that Raman spectroscopy have a good chemical sensitivity, so it can identify different structures. However, Raman spectroscopy, as I described previously, is very rare, very weak. So in fact, here is a Raman and fluorescence spectrum from zinc phthalocyanine. So you can see a very large fluorescence background and just super small, very weak Raman signals, both in the anti-Stokes region and the Stokes region. So Raman is very weak. So in fact, it's about 10 to the 14 times weaker than fluorescence and about 10 to the 10 times weaker than IR absorption. So it's difficult. It was very difficult to measure Raman, but of course, recently the detection mechanisms, better cameras, better filters allow us to detect Raman very easily. But in general, it's very weak. Moreover, the Raman being an optical technique, it's limited by the so-called diffraction limit, wherein the minimum distance you can detect between two signals, 2 points in the spatial, is about half the wavelength. So this means that if you use, say, visible light, the maximum spatial resolution you can get is in the hundreds of nanometers. And it's being the nanoscale materials in the 1 nanometer range is difficult to study with Raman, with the conventional Raman spectroscopy. That's why there are several techniques that are used in order to attain nanoscale resolution and also to enhance the Raman signal, to make the Raman signal stronger. So one of those, of course, there are several, as I said, but one of those techniques is tip-enhanced Raman spectroscopy. It was first introduced in a conference in 1999 and published in 2000 by these three, and there's one more. And tip-enhanced Raman spectroscopy is done, but basically you shine the light and detect the Raman signal, but you add a tip of a scanning probe microscope, for example, the scanning tunneling microscope or the AFM. So by putting the tip close to the molecule, you will get a very strong signal. For example, here, they found that when the tip is totally retracted, so when the tip is far, they could not detect the Raman signals. But when they approach the tip near the surface, near the molecule, they could easily get several Raman signals. And this enhancement, so the signal becomes actually infinite enhancement, but it's the amount of enhancement is debated how much. But basically, the source of enhancement is important. So why does this signal become stronger? So at present, there are two well-established reasons for the enhancement. And these two reasons are, one is the so-called electromagnetic enhancement. So basically, when you have the, it's like a nano antenna. So basically, the incident and scattered radiation are enhanced because they are isolated in this very small region, but also because of the plasmons present at the tip sample junction. So this is the so-called electromagnetic enhancement, but there is also one more so-called chemical enhancement, more popularly known as charge transfer resonance, wherein instead of the direct excitation from the molecule's lowest, highest orbital and lowest unoccupied orbital, you can, by placing the molecule near a metal, as what is always done in TERS or SIRS, you can get another source of electrons, charge transfer resonance in this case. So TERS is, Raman signal is enhanced in TERS because of these two effects, and these two effects happen simultaneously. One, you cannot do TERS without both of them, at least previously. So, but in fact, in TERS, it's mainly based on form of resonance. So here is some, the equations of Raman spectroscopy is very complicated, but this is, here is the intensity of Raman signal, and here is, so in the intensity, there are several terms, but I'd like to focus on this term, because this term you can for now ignore. So this term is the so-called Raman tensor, or the Raman polarizability tensor. So the important point is that this term is the vibrational, the energy of the vibrational mode, and this term, is the energy of the incident light. So basically, from this equation, it's easy to see that when the energy of the incident light is equal to the energy of the excited light, energy of the incident light is equal to the energy of the vibrational mode, then this term is maximum and the Raman signal is very large. So in such a case, this is the so-called resonance Raman effect. And actually, the TERS is mainly resonance with the excitation. So of course, there is so-called the ground state chemical enhancement, wherein just by placing the molecule in the environment, in the chemical in the metal environment, the Raman signal is slightly increased. But mainly, if you choose the proper wavelength of light, you can have a resonance enhancement by the intrinsic molecular states. So you excite the molecule from its HOMO to LUMO. Then you have resonance, the molecular resonance Raman. And as I said before, charge transfer resonance is when your energy is equal to energy of the incident light is equal to this energy. So you have a so-called charge transfer resonance. And this tree is the so-called chemical effect. And the other one is the plasmon resonance effect, where your molecule, your metal has a certain plasmon resonance, and the excitation is in resonance with that plasmon energy, and then you can get another enhanced signal, basically from these equations. So in general, TERS, or the enhancement in TERS, is defined by basically the resonance, or the how far your mode is from the energy of your laser or your excited light. So TERS has been used extensively since 2000, and some examples of materials studied by TERS is this one. So this is only for scanning tunneling microscope based TERS. So here is a example of TERS mapping. So these are carbon nanotubes. And the authors found that the carbon nanotubes has strong defect signals at the end of the carbon nanotubes, and the spatial resolution they were able to reach is about 1.7 nanometers, even in ambient conditions, so room temperature and atmospheric pressures. But also so this was reported in 2014, but in 2013, the first ultra-high vacuum low temperature, but only in liquid nitrogen temperature was reported. Here they investigated single molecules. So for a long time, it was theoretically predicted that because Raman is very chemically sensitive, and with the with the scanning probe microscope, the spatial resolution approaches nanometer or even angstrom scale. It was initially theoretically predicted that you should be able to identify, or if you take the Raman map of a molecule, then individual Raman modes should be different. So it should have different appearance. Because, for example, one Raman mode only vibrates the outer benzene rings, or one Raman mode only vibrates the inner benzene rings, but the signal therefore should only come from the inner part of the molecule or just the outer part of the molecule. Then it was expected that you can differentiate the vibrational mode from the Raman map. But in 2013, although this is the first report of that, they tried single molecule, really single molecule, just one molecule in a 3x3 nanometer area. They could detect the Raman signal, but unfortunately, they couldn't resolve the different vibrational modes. So it was a good result, but it's not complete. And several years after, the next one was in 2019. And in this situation, they were able to show that individual vibrational modes have different Raman maps. So in this figure, this paper was published in 2019 in Nature. So again, this is in UHV, but this time temperature is lower, 6 Kelvin. And then they found, so top one is the Raman maps. So they moved the tip across the sample and across the substrate. And then they found that individual modes show very different Raman maps. So this mode only at the center. This mode shows a cross. So here is the molecule they studied, cobalt tetraphenylfluoripyrin, I think. And they show different forms or different. They show that the Raman signal is strong only in distinct areas of the sample. So this result was very groundbreaking last year, and it finally experimentally verified the theoretical predictions for very long, that was predicted very long time ago. But however, in this work, in order to achieve this great result, so in fact they have about 2 angstrom of spatial resolution. So it's, as you can see, you can separate or individually identify from one small molecule. Note that this molecule is about 2 nanometer, I think. So it's very small. And then, so you can detect the signal, difference in signal within the angstrom scale. However, in order to achieve this, they had to approach the tip. So as I mentioned before, you have to put the tip. And in this work, in order to achieve that great spatial resolution, they had to approach the tip to the molecule. And in fact, they themselves said within subatomic separation. So the distance between the molecule and the tip is very near. And although this have shown good spatial resolution and very strong Raman signal, in fact, the Raman peaks are affected. So that is, here is a gap distance dependence. So this is the separation between the tip and the molecule. And red dots are the Raman signals. So as you can see, when the tip is far, for example, this mode has 3025 wave numbers. And then as they approach to 2 angstroms, so this data were taken at 2 angstroms separation, the 3025 mode actually became a 3003 mode. So this means that with this technique, although you can get a very good spatial resolution and very strong signal, it's difficult to assess the original properties of the molecule because the measurement itself changes the molecule. And they admit this problem. Well, they didn't point this out as a problem, but they admit that basically the molecule become a hybrid system of the molecule and the tip. But if we want to assess the molecule itself, so then this technique is, we cannot use this technique. So in order to solve this problem, so the conventional technique was just to place the molecule directly on the metal and then approach the STM, the metal's tip. In our case, what we did is we placed an insulator, sodium chloride, in between the metal and the molecule. So in this situation, the metal, the molecule doesn't interact with the metal, and we carefully did not approach the tip very near the molecule. Moreover, our technique could allow a variety of measurements to be done on the same sample while also keeping the original electronic structure. So when you put the molecule near the metal, the molecule's electronic states hybridize with the metal, and therefore you cannot get the original electronic structure. But as I will show earlier, with this technique, the original electronic structure is preserved, so we can study the original properties of the molecule. So as I said, our technique is based on the STM. So we use the low temperature ultra high vacuum STM, and this STM is a little special. So we have lenses inside the UHV, inside the ultra high vacuum chamber, and this is for detecting light and introducing light into the STM tip junction. So here is a schematic of the setup. So we use a continuous wave tunable laser, and then basically just detect Raman. So in fact, there's nothing so special about this setup. So we deliver the Raman signal to the STM via optical fiber, and then just detect it using conventional techniques. So we illuminate on one side and then detect on one side, and then approach the tip to that spot. And for our experiments, we use the copper naphthalocyanine molecule. And in this case, we place the copper naphthalocyanine molecule on a sodium chloride surface, as I said. So just deposit the molecule on the sodium chloride supported by silver surface. Then here is a STM image of that molecule. So here's a large scale scan showing several. So scale is about 100 nanometer. And these dots are the copper naphthalocyanine molecule. And as you can see, they are present on the sodium chloride. These are sodium chloride, and also present on the silver. And I'm interested in studying the molecule on the sodium chloride. And when I check the single molecules on the sodium chloride, so these are individual sodium and chlorine, individual chlorine atoms. So we found three different, so we found that the molecule can absorb on the surface, so it can be present on the surface in three different configurations. So it can be parallel, this axis parallel to the chlorine, or perpendicular to the chlorine, or at some angle. But I found that of this species, this one I call the 45-degree molecule is the most abundant. So in this presentation in our work, we just focus on this molecule. So then we measured the Raman signal, the TERS signal of our molecule. So we put the tip near the molecule, and when the tip is at the center, here there is no signal. But as we approach the tip off center, then we can detect the Raman signal. And moreover, away from the molecule, we cannot detect any signal. So basically, this suggests that we successfully got the tip-enhanced Raman signal. Also, surprisingly, actually, we wanted to compare this signal because this is our technique basically, and this is the usual way to measure TERS. So when we place the molecule on the, when we place the tip on the metal, on the molecule on metal, we couldn't find any Raman signal. So it's quite surprising considering that this is what was previously done. So in order to investigate this point, we check the electronic states of the molecule. So scanning tunneling spectroscopy allows us to measure the electronic states of the molecule by measuring the current or the change in current as we change the bias voltage between the tip and the sample, between the tip and the substrate. So in the STS signal, so here are two scanning tunneling spectroscopy spectrum. And when the molecule is on silver, we were only able to find one peak. And whereas when the molecule is on copper naphthalocyanine, we found two peaks, one on the positive side and one on the negative side. And based on STS calculation, based on calculations, this can be identified as this one is the LUMO, or the lowest unoccupied molecular orbital, and this is the HOMO of the molecule. So in this case, also we found that when the molecule is on the NaCl, when we change the bias voltage to around 1.85 volts, we can see this kind of structure, which when we compare to the calculated molecular orbitals, they look exactly the same, basically, suggesting that also the LUMO looks the same as the molecular orbital, whereas if we change the bias voltage for the molecule on the metal, the molecule's image doesn't change. This means that the molecule is hybridized, or the molecule's electronic state is hybridized with the metal. Whereas for the molecule on the NaCl, the molecule is electronically decoupled from the metal surface. So the DFT calculations confirm that the molecule is in its original electronic state, which is very important in our experiments. Whereas the molecule on the metal, it's hybridized with the metal. Then what does this imply? So as I said before, there are several sources of enhancement in TERS. So first is the electromagnetic enhancement. So however, as I said, the molecule on the metals show no Raman signal. But in this experiment, we just moved the tip from the molecule on the sodium chloride to the molecule on the metal. And basically, there is signal here and there is no signal here. So if this means that this observation cannot be explained just by the electromagnetic effect, because the same tip is used and the same energy of the laser is used. So this electromagnetic enhancement cannot answer why there is signal here and no signal here. Also, chemical enhancement cannot be the reason, because as I said, there is no hybridization. So it means there is no channel. There is no charge transfer channel between the metal to the molecule on NaCl. So the chemical enhancement is absent, or if not really absent, it's very much reduced. So to explain our results, one more possible reason is just the direct molecular resonance. That is, instead of charge transfer, instead of tip to molecule directly, then there is just we excite the molecule by choosing the proper excitation light. But in order to confirm this, we have to determine the absorption spectrum of the molecule. So I'm sure many of you are familiar, but it's quite easy to measure the absorption of a molecule if it's on the solution or in solid form, but it's very difficult to measure the absorption of one molecule. So, but our group was able to introduce a technique wherein, so in the absorption measurement, the conventional absorption measurement, you shine the white light to the molecule and then measure the absorbed signal. In our group introduced this technique, so-called scanning tunneling absorption, wherein the plasmon resonance, also the localized plasmon at the tip substrate junction, Also, it has a broad spectrum. So basically, Imada-san, one of our group members, used this light as the light source for absorption measurements. And then he found that when the molecule, when the tip is near the molecule, there was some dips in the absorption spectrum, in the scanning tunneling luminescence spectrum, and no dips in the when the tip is far. This suggests that when you divide these two signals, he was able to get this. And through calculations, they found that these two features correspond to the absorption of the molecule. So it's one of the first demonstrations of single molecule absorption. And we applied this in order to confirm our results. And we found that, yeah, for the molecule and the metal, there were no signals in the vicinity of the excitation light we used. And then when we placed the molecule on the sodium chloride, we could easily detect this dip, which corresponds to the absorption of the molecule, as also confirmed by room temperature UV-Vis measurements in solution form of this molecule. So now we know the absorption spectrum of the molecule, we can perform resonance Raman spectroscopy. So what I did is I varied the laser wavelength, excitation laser, around the absorption of the molecule. And by doing this, as I showed before, that the Raman signal is very sensitive to the incident light energy, I found that the energy, the Raman signal changes a lot, and that when the energy is lower than the absorption of the molecule, then almost no signal. And then, so when we plot one or some peaks here, we can observe that the intensity varies exactly as the absorption of the molecule. This simply means that when the molecule is excited at its absorption, well, it shows maximum or very strong Raman signal, as is expected for resonance Raman spectroscopy. So actually, this is direct evidence of resonance Raman effect at really a single molecule, because in this experiment, we can only see one molecule. So aside from this evidence of resonance Raman, we also tried to perform Raman mapping. So we measured the Raman signal at several points of the molecule. So here, we can see that when the tip is placed here at the between two lobes, then this is the Raman signal. And when the tip is placed at this, we can observe this Raman signal. So very clearly, these Raman signals are a little different. So in fact, when we do the Raman mapping for this mode, we found this signal. So Raman signal is like this. And then this mode, Raman signal is like this. And in this mode, the Raman signal is like this. So we could identify 3 different Raman maps, 3 different patterns of the TERS maps for all of these vibrational modes. So in order to see why or how this happens, for example, this mode, 1389 modes, by comparing with the DFT calculations, we found that this mode, the 1389 mode, has these vibrations. And our explanation is that when you place, so this mode has a symmetry of B1G. And when we place the molecule along this symmetry axis, so for example, here, when the tip is here, these 2 modes are vibrating in phase. But when the tip is placed here, modes here and modes here are vibrating out of phase. So we propose that when the modes are here, when the tip is here, this modes is enhanced. And when the tip is here, these modes are canceled. That's why shape is like this. So enhanced signal here, and reduced signal here, 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 and at the center. It's the same for this mode. For example, this mode, the symmetry, so the mode is like this, and the symmetry axis is like this. And then again, when the tip is here, these modes are out of sync, out of phase. And when the tip is here, the tip is in phase. Vibrations here are in phase. Therefore, this should result in such a Raman pattern. And lastly, this mode showing circular pattern, we found that this mode is so-called A1G mode, and this is basically totally symmetric mode. So wherever you place the tip, there is a maximum Raman signal, or there's a strong Raman signal, suggesting that that's why the pattern is like this. So therefore, we propose that the Raman maps we observe is defined by the symmetry. So there are 3 different symmetries of this molecule we found, and the Raman maps show that it's sensitive to the vibrational symmetry. So finally, in summary, in our work, we were able to demonstrate resonance Raman scattering, resonance Raman spectroscopy at the single molecule scale. And next, we were able to confirm that the Raman maps reveal the vibrational symmetry of the molecule. So I'd like to thank my lab mates, my co-authors, especially Dr. Kim, Dr. Imada, Dr. Hezawa, Dr. Yang, and Dr. Kazuma. And our results are supported by the theoretical work of Dr. Miwa, former member but now in Northwestern University, and the group of Taketsugu Sensei in Hokkaido University. Also, I need to acknowledge these funding agencies. So as RIKEN's program for junior scientists, and Kakenhi for my grant in aid for early career scientists grant. So yeah, that's all. Thank you.
Thank you very much, Raf, for that nice talk. Questions? Sabi na nga ba kulang yung 2.5 hours pag ano ng speakers? Wala ka pang masyadong sinabi niyan, ha?
Oo nga, sir.
Alright. Okay lang. Okay lang. That's why we have this limited number of speakers for things such as this. Questions from the audience?
Ako na muna to start the ball rolling.
Sige.
Si Mo.
Go ahead, Mo.
Hi, ma'am.
Hi, Raf. Yung single molecule, I'm just curious kung paano mo siya nata-target yung position in your slides. If you focus on, or if you put the tip at that particular position, so paano yan nakikita? From what I understand, di ba yung image, makikita mo post-processing na? Or may image ka na as you measure the absorption or Raman?
So, sandali lang po. So actually, yung pong aming Raman signals, so this is STM image po ng molecule. So it's the topographic image of the molecule. And then actually, this is taken simultaneously with this Raman map. So at the same time, we can measure the topography and the Raman signal.
So this is a single shot? So
opo, basically single shot.
Not raster scanned?
Sorry. Hindi po siya single shot. Instead, so yung tip po namin is minumove namin across like this. So raster scanned, as you said. And then we measure the spectrum at every point.
I see, okay.
And then post-processing, yes, you're right.
And then locate that particular position.
Yes po. Then you can...
For the corresponding Raman, okay.
Yes po.
Okay,
But,
got it.
Of course, for the other spectrum like this po, just by... we can very precisely place the tip here, actually. Sorry. We can very precisely place the tip at a certain point in the STM box. So especially the UHV low temperature STM is very, very stable. So you can, there is almost no drift. So the molecule stays in this spot for example, in that spot of the substrate for a very long time, and you can place the tip at a selected point, and then it is at that point, basically, mainly
Okay.
because of the node drift.
Thank you. Thank you.
Raf,
Yes, sir.
you mentioned something about, thanks, Mo. You mentioned something about plasmon effect.
Yes, ma'am.
So does it have any bearing whatsoever with how the optical properties of the material that you use for the tip should be in relation to the substrate or the sample that you are trying to image?
Yes,
Should there
yes,
be
sir.
an effect?
Yes, sir. So basically, this molecule was chosen. Sorry. So maybe I didn't describe it completely. So in our experiments, po, the substrate, the tip we use is gold, and then the substrate is silver. Well, the substrate really, if we would have wanted to use gold, but we found that it's very difficult to prepare the sodium chloride on gold, so we didn't use gold. But anyway, as you said, the plasmonic properties of the gold is very good in the 700, 600 to around 800 maybe nanometer range. And the absorption of this molecule is known to be in that range. So that's why gold tip plus the 700 to 800 nanometer laser plus this molecule is the good recipe, as you would say. So yes, it depends on the choice of the molecule, the tip, and the incident light is mainly because of the plasmon, or one
Alright.
of the most important choices you have to make.
Okay. Thank you very much, Raf, for clarifying that. I think we have a question from the chat. I think Ma'am Julia Salor, you can actually unmute yourself, but if not, this is the question, Raf, for you. Well, what is the significance of the study and how Raman spectroscopy can contribute to future studies? I would assume in terms of molecular science and imaging.
Yes, so so Raman spectroscopy is widely used for identifying, say, medical molecules, possibly for use in medicine, or say for use in electronics. And basically, the interaction of a molecule on a solid surface is an important point, an important topic in the field of semiconductor, for example. So how does a molecule adhere to the surface, or how does so for example, in a battery, there is the solid surface, the electrode, and then there is the liquid, or you can have a solid state battery, but basically there is an interface. So there is a adhesion between the molecule and the surface. And this adhesion is the properties of this adhesion is very important because it will allow us to improve this interaction, and therefore we may be able to find new ways to use such a molecule metal or molecule insulator combination. However, if we want to so not however, but for the case of tip-enhanced Raman, so the tip-enhanced Raman can be powerful in studying these interactions because it can identify the presence of the molecule, and also it can identify if the molecule have changed its properties by attaching to the surface. So this point is quite important for nanoscale materials. And also, for example, if organic chemists are trying to make a new material, make a new chemical compound, most of the time they are not so sure about, well, of course they know, they have a guess of what could happen, but they cannot be so sure of the result. But using our technique, they can at least identify if the molecule is symmetric, and symmetry is also a very important aspect in such kinds of research. So these kinds of things makes this work important, I think. Thank you. Anything else?
What's so interesting about sodium chloride on silver?
Sodium chloride on silver. Actually, ma'am, I would say that the sodium chloride on silver surface is a nice template for studying insulator metal molecule interface. So because the sodium chloride is easy to make in the lab, basically very easy. So that's one point. Of course, the sodium chloride on metal is also a topic of interest for theoretical chemists, because they, for example, in this image, in this image, we can see there are dark bands and bright bands. So this surface, silver, is a silver 111. So the topmost surface has a 111 crystal facet. Then the sodium chloride is actually 100. So in fact, there is some, there is a small mismatch, lattice mismatch between these surfaces. So then that's why this dark, light and dark bands are appearing. So the sodium chloride on silver can be used as a template for studying such small interaction, small defect. It's actually not defect, but a small mismatch of the lattice. So basically, it's a template for studying these kinds of things, I think.
Okay, thank you.
Thank you, po.
Chase, last question.
Sige. Kuya Raf,
Yes.
would the result be the same if, would your conclusion be the same if, di ba yung tinignan mo is yung 45-degree na molecule lang with respect to the silver?
Yes.
Would the conclusions be the same if you use yung 0 degrees or yung 25? I'm sure nakaano yun.
Yeah, so I think in general the conclusions are the same, but they can be a little different. Of course, I only looked at this and I only reported on this, but in fact, I have the results of this one, and I'm not ready to describe them.
Magkaiba yung selection rules eh.
Sir?
Magkaiba yung selection rules.
Yes, magbabago po yung selection rules, and actually the main difference, maybe it's not obvious here, but this molecule is sitting on the chlorine. So the copper is on the chlorine, but in this case, the copper is on the sodium.
I see.
So this small change in the bond between the copper, sodium, copper, chlorine affects the Raman signal, I think. Can affect it. So very small change, but there is some. But basically, it's still in resonance, and it's still, I think it will still show the symmetry.
Okay. Thanks. I think we have to move on to the next speaker. Thank you very much, Raf. But before we let you go,
yes, Bob.
I would like to read this certificate of appreciation.
Oh.
There is this guy here. Okay. Kita na ba?
Yes, Bob.
All right. Allow me to read this one quickly. The Philippine-American Academy of Science and Engineering presents the certificate of appreciation to Dr. Rafael Jaculbia for delivering the lecture entitled Tip-enhanced Raman Spectroscopy and Imaging of a Single Molecule in Ultra-High Vacuum and Low Temperature Environments on 23rd July 2020. Should be 2020. As part of masyado ng madaming COVID. As part of parallel session 2.2 during the 40th PAASE anniversary and 2020 APAMS, Manila, Philippines, signed by Dr. Gisela P. Concepcion, PAASE President, and myself as host. Thank you very much, Raf. You will get a hard copy of this one as soon as they allow us to go to, or you go back to the Philippines. Maraming salamat.
Salamat po.
All right. So